All right, let's do a problem or two from section 5.3. Let's do number 5 or something similar to number 5 for you. Diagonalize the following matrix. And they give us the matrix and they also give us the eigenvalues. So let's see. Here's the matrix. Okay, so let's recall the big theorem in this section. It's the diagonalization theorem, and it says this. It says A can be written in the following form. Some diagonal matrix is D, so it can be written in the form P times some diagonal matrix times P inverse if and only if the columns of P are linearly independent eigenvectors and the diagonal elements of D, all the rest of them are 0, are their corresponding eigenvalues. And I'm talking about the eigenvalues that correspond to the linearly independent eigenvectors. So in other words, P might be something like this, and D might be something like this. It's a diagonal matrix. Well, the first eigenvector has to correspond to the first number in the diagonal of the matrix, so 2. So this would be the eigenvector for 2, this would be the eigenvector for 5, this would be the eigenvector for 7. So they have to correspond with each other. There's also a P inverse over here, but that's essentially the theorem. So A can always be written in that form if and only if every one of the columns of the first matrix P are eigenvectors, and all 3 of them are linearly independent. If there are n of them, then they're n linearly independent vectors. And every one of these numbers along the diagonal of D is an eigenvalue that corresponds to one of these vectors in order. Okay. So let's try to keep that in mind when we solve this problem. So notice they've given us the eigenvalues directly, 2, 3, and 4. So what I'm going to do to try to answer the question, I think they've already told us the answer, because it says diagonalize the following matrix, so we must be able to do it. But I'm going to find the eigenvector that corresponds to 2, the eigenvector that corresponds to 3, and also the eigenvector that corresponds to 4. And then I ought to be able to form the first 2 matrices. And then to get P inverse, I'm just going to take the inverse of this guy. All right? So let's find the first eigenvector that corresponds to 2. So remember, in general, x is an eigenvector for the eigenvalue lambda if it satisfies this equation. Okay. So for our particular problem, A is 666, -2, -4, -8, 0, 3, 7. There's x, and for lambda, let's try 2. So I suppose that's one way to write it. So remember, we always put these things in the following form: a minus lambda I times x equals 0. So let's write out this determinant. So remember, you just have to subtract 2 from all the diagonal elements, essentially, to get this matrix. So that'd be 4, -6, 5. All the rest of them are the same. All right. Okay, and here's x. So we're solving this thing for x. And so as always, we write down the augmented matrix of the system and look for solutions. So I will insert a column of zeros there. Let's put this thing in reduced row echelon form real fast with a calculator. And this looks like a 3x4. So this is equivalent to this matrix. Okay. So let's try to interpret this. And it looks like we have infinitely many solutions here because we have a free variable. But let's try to express that solution set. Because it looks like x1 is equal to 1/2 x3, and it looks like x2 is equal to x3. Okay. So our general system looks like this. And if you factor out the x3, well, clearly the eigenvector associated with that eigenvalue is 1/2, 1, 1. Okay. So we're going to do the same thing for the other two eigenvalues, and we're going to find the three eigenvectors that way. So let's move on to the second eigenvalue, which is 3. So this time we want to consider this system. Okay. So I'm just going to subtract 3 from all the elements of the original A, which is right there. So here's this matrix, 3. All the rest of them are the same except for the diagonal elements. And we'll make the right-hand side 0. Try to keep these guys in order. Once again, calculator to put it in reduced row echelon form. That'll give us our second eigenvalue, or I should say eigenvector. All right, so this is what I get. So once again, one free variable, and the system looks like this. And remember, this is for our second eigenvalue. It's just x1 equals 2/3 x3, and x2 equals x3. So here's our arbitrary solution. Take out the x3, it looks like the second eigenvector is 2/3, 1, 1. That's the second one, okay? That's the second column of matrix P. We already know what the diagonals of D are because they gave us the eigenvalues. But now let's move on to the last eigenvalue given, which is 4. Okay, so the last eigenvalue is 4. So let me subtract 4 this time from all the diagonal elements of the original matrix, which remember is this guy. So subtract 4 from the main diagonal elements. get this. All right, now calculator. So here is my reduced echelon form. So once again, one free variable, so it looks like x1 equals 3 halves x3, and x2 equals 3 halves x3. Okay, so and x3 is just x3. So factor out the x3 as always. So 3 halves, 1. So that is eigenvector number 3. Okay. All right. Now in the problem, they give us the D, and we kind of knew it already. They give us this for the D. So when you do the P, just make sure that you make the eigen, or the columns, correspond to the correct eigenvalues. And let me show you what I mean. So remember, this thing is diagonalizable, which means we can write it like this. And we already know D. They gave us D because they gave us the eigenvalues. There's our D. All right. So once I get the P, I can find P inverse easily. But for the first column, just make sure it matches up with the 2. So that's the first eigenvector that I found. So let's see. I go back, and it looks like that was 1/2, 1, 1. And now the 3 is the second one I found, and that was 2/3, 1, 1. And for the 4, that was the very last one we did. That was 3 halves, 1. Okay. And I suppose we could find P inverse if we wanted to. But these guys should be linearly independent if we did that right. But I might just find the inverse of this matrix real fast just to make sure. It's a 3 by 3. Well, the inverse of this thing does exist. It's -6, 10, -6. And then this is 6, -12, 9. I just found the inverse of this thing with the calculator. I'm not sure if the computer asked me to do that, but I went ahead and did it anyway. So here's my P, here's my D, here's my P inverse. And they're really just going to ask you for the P, I suppose. But you can always find the P inverse if you wanted to. And you can always check this thing, I suppose, by multiplying all 3 of those together and making sure you get the original matrix, which we're calling A. But that's it. We just had to find the P.